In this video, I'm going to walk you through some examples of how to write electron configurations using the periodic table. I'll also give some examples of orbital box diagrams and abbreviated or shortened electron configurations. So let's just start with some electron configurations, and I would like to start at the top of the periodic table with sodium. So here's sodium right here. So the first thing, if you're writing electron configuration using the periodic table, find the element on the periodic table. Now, you will look, when we write a full electron configuration, we always start at the top of the periodic table. Now, what we need to recall is that the energy levels are determined by the period or row that the elements are in. We do need to note that when you get into this middle where the transition elements are, that the energy levels decrease by 1. So if you're in row 4, the energy level is 3. Over here in the P sublevel, it's the same as in the S sublevel. The energy level is the same as the period that you're in. And we won't be doing electron configurations, although sometimes I'll ask one as one of your choices for extra credit. But if you were to go down into the F, their energy level is actually 2 less than the period they're in. Now I'm going to erase where I highlighted because I want to be able to see those numbers. So as we're writing the electron configuration, we're starting where hydrogen is, and we see that we're in the first row, which represents the first energy level, so I write 1. The first 2 columns are in the S sublevel. Now on the first period, they're separated from each other, but that's okay. And then you use the boxes to count how many electrons would be in that sublevel. 1, 2. Now the S sublevel can never have more than 2 electrons, and that is because the S sublevel only has one orbital, the S orbital, and each orbital can only hold 2 electrons. So anywhere you have an S, just remember you can only have 2 electrons. Of course, if you're using the periodic table, you won't forget that because the S is 2 columns, so then every time you move to a row, you only have 2 electrons that can fit there. Then we're done with the first row. Every electron configuration after hydrogen starts out 1s2. That's what the first row, when it's completed, looks like. So we go down to the second row, or the second period, and so that represents energy level 2. Now we're going to come in here, which is the S sublevel, and we count, and we have 1, 2 electrons. Now you do have to be careful. You go all the way across. Don't start going down the table until you've completely filled a period. We're still in the second energy level. The p orbitals, their energy level is the same as the row or period that you're in. I'm going to rewrite the number 2, and now we're in the p's. So the p's are represented by the 6 columns here. And so when you completely fill a p, you'll use 6 electrons. 1, 2, 3, 4, 5, 6. Now, if I were to stop right there, wherever you stop, that's the electron configuration for that element. So right now, what I have written is for neon. But neon is not where I'm stopping. I want to go to sodium, so now I'm in the third period, which would be represented by the third energy level. I'm back in the S orbitals, but I'm only going to go in 1. And that's because sodium is the first in the third period. And so right there, this is the electron configuration for sodium. Now, another common thing we have to do is look at the valence electrons. Valence electrons are the outermost electrons. So they're electrons in the highest energy level by definition. So when I look at the energy levels represented in this particular configuration, there's the first energy level. Here's the second energy level. It includes the 2 S's and 2 P's. The big T2 is what is represents the energy level. And then there's the third energy level. So we have the first energy level, the second energy level, and the third energy level. The third level would be the highest, and so our valence electrons are in the 3s1s. 3s1, I guess. So the configuration of the valence electrons is 3s1. The number of valence electrons is just 1. Now, if the question only asks you how many valence electrons for the main group or the representative elements, all the tall columns, it is really very easy to figure out the valence electrons just by looking at the group identifier. So I see a 1 and then a 1A. So the number in front of the A tells you how many valence electrons. And then the number 1 would also tell you. If the number is greater, well, on the A's, it goes from 1A, 2A, and then do you see it comes over here to 3A? So, but that's group 13. You subtract 10 from this side of the table if you're using the top number. But you can always use the bottom number. So let me state it again, and then we can look at one too. But for example, sulfur right here, if I look, it's in 6A, so it has 6 or 16. So 16 minus 10 equals 6. So all of them on this were above the P sublevel. If you're using the numbers 1 through 18, you have to subtract 10 from the number to get the valence electrons of the representative elements. All right, so that's our first example, sodium, of an electron configuration and identifying valence electrons. After I go through several examples, I will then switch. I will go and work on an orbital box diagram, explaining that, and then the abbreviated form. So let's try another one. This time I'm going to go down into the transition metals. So I think I will go down to nickel right here. So I'm going to do a fully written out electron configuration. So that means you always start up at the same point. What it means for you as you practice is there's a pattern, because as you go down the periods of the periodic table, the configurations are always going to be the same. The difference will be where you stop, and you'll stop at the element that you're looking for. So let's try. We say, okay, we're in the first energy level. We're in the S sublevel, the first two columns or groups, and there's 1, 2. Remember, they all start this. Okay, I want to move over 1, 2. I want to move over this. Move this over just a little bit. 1, S, 2. Okay. Then I go to the second row, which represents the second energy level. 2. These are the S's. S, 1, 2. And you don't have to write as much as I am writing on the periodic table. You can do this in your mind. I'm only writing because since I can't see you and you're just looking at this whiteboard, I want you to see what I'm kind of writing so you can see what I'm looking at. So then I know I can't keep going down. I've got to finish the whole second level. So I come over here. Here I'm still in the second energy level, but now I'm in the P sublevel. So the P sublevel goes all the way across. We know it's going to be all the way filled up because we have to get further down. And so P's, since they have the P sublevel has 3 orbitals, it will hold 6 if it's electrons if it's completely full. So if you count across the boxes to get to neon, it would be 6. So that's the second period. Now we go down to the third, which represents the third energy level. And I'm going to be in the S's. If you go across the S's, they will always have 2. They can have a maximum of 2. That's because the S sublevel only has 1 orbital in it. Then we don't skip the empty space. Like, keep going. Now I'm in the third energy levels of the P's. And I'm going to go all the way across to get to argon. So that would be 6. So right now I would be at argon. So if I stopped here, this is the electron configuration for argon, but I'm not going to stop here. Now you might think that we would go 3s, 3p, and then 3d. But if you follow the periodic table, you'll see we go down to 4, and we're actually in the s's. So the s's come before the d's. And this has to do with how the orbitals overlap each other. The electrons don't care that we've numbered them, so they go in. What the electrons do is go in from the lowest energy to the highest energy. It's called Aufbau principle, which is in German just meaning like building up. So even though we know numerically, we think, oh, 3s, 3p, 3d, the 4s sneak in there because they're slightly lower in energy than the 3d. So we get 4s2. And now what you notice is in the d sublevel, the energy level is 1 less than the period or row that it's in. So these are now 3ds. And we will go to nickel. So let's count. If it was full, there would be 10, but this is not full, so it looks like 8. 1, 2, 3, 4, 5, 6, 7, 8. And so that would be the electron configuration of nickel. Now, there are some exceptions in the filling rules of the electron configurations. For our introductory class, we won't be thinking about that too much. We just want to become very competent at doing some electron configurations. So let's look at the energy levels to try to identify the valence. So I have the first energy level there, the second energy level, the third energy level, which includes this, and then finally the fourth energy level. So it is, by definition, the valence electrons are in the highest energy level. So in this example, 4, the fourth energy level, would be the highest one. So its configuration is 4s2, which means this transition metal has 2 valence electrons. The transition metals, the ones that are in the D sublevels, their chemistry is, they have a little wider range of things they can do, in part because they have 2 energy levels that are not complete. Like the third energy level, in this example, the fourth energy level is not complete, and the third energy level is not complete. So what we find, just a few observations, is that sometimes with their trends, they're not as dramatic as the representative elements. They tend to have some trends, but they might be a little steadier. Their chemistry is can have a little more variation in terms of what's going on. And some of their bonding can be a little bit different. So the transition elements have variation here. That in our class we're going to focus on the representative elements, but we will do a few things in the transition elements, and we just see here as an example of variation that they have this third level, then fourth level, then back to the third level again. Okay, so we're going to try another one. And then we'll start thinking about the other 2 things I mentioned, the orbital box diagram and the abbreviated form. So I want to go even further. Why don't we go to bromine right here? So again, if I'm doing a fully written out electron configuration, this is where I would start. Now, you can at any point pause it and see if you can write it down, but I'll work through it. So I'm in the first and the S, and I count 1, 2. Then I go to the second level, I start in the S and I go 1, 2. I go across to here. Now I'm in 2P and I go 1, 2, 3, 4, 5, 6. Okay, now I go to the third level. I'm in the S and I go 1, 2. Then I go all the way across. Here I am again, 3P, and it's going to be 6 because I'm going all the way across. 1, 2, 3, 4, 5, 6. That gets me to argon. Okay. Then I come here for S. 1, 2. Then I go 3, D, and it will be 10 because D sublevel has 5 orbitals, which is 10 electrons. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Then I come back into the 4. I should have started further to the left. These are the P's, and I go 1, 2, 3, 4, 5. And I'm going to stop there because bromine is right there. So you can see how this is getting long, and it could even get longer if I were further down in the periodic table. Let's take a look at where our valence electrons are in this configuration. So I have the first level here. Remember, valence electrons are the highest. The second level is all of that. The third level is here and here. And then the fourth level is 4s2 and 4p5. So even though they're split, they're both in the same energy level. So the configuration of the valence electrons is 4s2, 4p5. So there's 2 electrons in the S and 5 in the P. So we have 7 valence electrons in bromine. In fact, every one of those elements in that group have 7. So a look here, if the question was just how many valence electrons, it's in 7A, which tells me 7 electrons. Or if you have the other numbering where it says 17, subtract 10 or look at the second number. So you can just look at the second number, I guess. And you also get 7. So bromine has 7 valence electrons. Okay, so now what we're going to do, you see how long this one is? Some of them at the top, like in class or in the video, I did nitrogen, and then I did sodium. Even the next one I did, nickel, wasn't awful, but we're getting to awful. But then you get to bromine, and it's so long. And once you're really good at this, you know it's so repetitive. And what we're usually interested in are the valence electrons. So we do have an abbreviated form of an electron configuration. So let's see about that. So in the abbreviated form, what you do is you go to the noble gas in the period before the element you're interested in. So let's say bromine. The noble gas, so noble gases are all right here. The last column on the right. And the noble gas before bromine is argon. And so in a bracket, I write the symbol for argon. Now, what it means to someone looking at an electron configuration with that notation is all the electrons to argon are present. It can only be a noble gas. You can't pick any random element. It has to be the noble gas in the row, or period is what we call it, before the element that you're interested in. So argon is the only choice for bromine. Then what we do is we write the electron configuration for everything in the period that your element is in. So then I would start on right here. I would say 4s2, 3d10, 4p5. And so you cut off the whole first part. You still are representing the 7 valence electrons because you have, there they are, there's your valence electrons. So it's still represented, but you don't have the first 3 rows to get up to argon. So you see how this can be helpful. Now you might think to yourself, yeah, that's great. Can I do this on every single one on the exam? Usually I have you write 1 or 2 that are in the fully written out electron configuration, no abbreviation. Then I'll ask you a third one, and it will say you may use abbreviated if you like. Okay, so I will give you an opportunity to use abbreviated, but I will also have problems that are the fully written out. Let's do another one that's abbreviated. What if we had barium down here? Okay, so if I were to do barium, I would, the noble gas, and just pause now, and I want you to see if you know the noble gas. So to figure out the noble gas, if barium's in 6, I go to 5, and it would be here. It would be xenon. So I'm just going to write here, this is bromine, and now we're doing barium. So I would put xenon in a bracket. Now remember, it has to be a noble gas, and it has to be the one in the period before your element. And then I would say 6s2. Now you could just, with your imagination, with the little you've done electron configurations, if I had to start at 1s2 to get down to barium, it would be a lot. So it's very helpful, especially for these large ones. And so there's my valence electrons there, and there's 2 of them, which makes sense because barium is in group 2A or group 2. Now I'm going to go up to the top of the table so you can see one that's up higher. Let's do, what if we did phosphorus? So for phosphorus, you would have to look at the noble gas in the period before it. So phosphorus is in period 3, so you would have neon as a bracket. Then you come down to the period you're in, which is 3, and you'd say 3s2, and then 3p5. And so for phosphorus, we have right there, those are the valence electrons. There's 7, why did I say pf5? I'm glad you probably were saying, what? It's not 5. What I was thinking is 5 valence electrons. It's pf 1, 2, 3. I kind of hope you caught me and wanted to tell me that I was wrong. Luckily, I caught myself before the end of the video. So it's 5 total valence electrons, but there's 2 in the S's and 3 in the P's. So I hope this gives you enough idea about electron configurations. So we have electron configurations. These are abbreviated electron configurations, or sometimes they're called noble gas electron configurations because it has to have a noble gas. Your book might call them shortened electron configuration, but in the bracket, remember, you have to have a noble gas. And now the last thing I'd like to do is just give you an example of something called an orbital box diagram. Now, we don't use orbital box diagrams too much in our class, but if you go on to the next level, chemistry, qualitative analysis, Chem 1, you will use orbital box diagrams when you're talking about different things, like to do with bonding. And so I think it's good that you at least see it now. Now, what I want to do is write an electron configuration here. So let's see. I'm just going to write nitrogen. 2p3. Okay, so here's nitrogen. And if you look, I'm just writing nitrogen there. So I just need an electron configuration to show you. You can practice writing them. So what box diagrams do is they use a written box, like you draw a box, to represent each orbital. Okay, and so one thing we need to remember is S sublevel. If these are the sublevels, and we have S, P, D, and F, then in each one, this has one of the S orbitals in it. This has 3 of the P's. D has 5 of the D orbitals, and F has 7. Okay, so we need to remember how many orbitals because that will tell us boxes. So how I envision orbital box diagrams is as a picture using boxes and arrows of an electron configuration. So if I have an S, that will have 1 box. And then the 2 says I have 2 electrons. So I have 2 arrows, one pointing up and one pointing down. Now I like to write which orbital it's in. Which sublevel it's in. A lot of people don't. They just leave it blank, but it helps me see. So that's what 1s would look like. Then I go to 2s. Well, S again is only going to have 1 box, and my boxes tend to get messy. This is never anything I would do for long electron configurations. Maybe if I was at the end of an electron configuration, like an abbreviated one. Well, I'll do one where it was abbreviated. So 2s2, so I have 2 electrons, so 2 arrows. They can be half arrows, they can be full pointed arrows, but one has to go up and one has to go down. And then we have the P's. Now P's have 3 orbitals, so it's going to have 3 boxes. I have another text that just draws a long rectangle and then does this. And so all of these right here are 2 P's. And I have 3 electrons. So the electrons, it's called Hund's rule, Hund, H-U-N-D. And they go into empty boxes before they pair up. So this would be 1, 2, 3. Now, if there was a 4th electron, it would come into the first box again, but there's not. There's just 3 electrons. So I have 3. These are unpaired, I can draw them full arrows, unpaired electrons. And why it does this is because an empty orbital is easier to get into than one that already has an electron, because remember, like charges repel. So if there's already an electron in one, then for another one to get in there would require a little bit more energy. So it has to do with whatever's the easiest in terms of energy as I think about it. So right there, what I just drew is an orbital box diagram. So let's do one. I want to do one. Let me look back here. So let's do for bromine. And I'm going to do it for the abbreviated. Okay, so if I was doing abbreviated, I wouldn't do the argon. And the reason I'm doing it abbreviated is because I just can't ever imagine doing that many boxes. So let's just do the valence, or the outermost level, or the period that bromine is in. So I have 4s, so S is 1 box. And there's 2 electrons in it, because I see that too. So 1, 2. Then I have 3D, so D would have 5 boxes. So all of these are equal boxes. They're all in the 3Ds, and they're all full. So how they would fill is 1, 2, 3, 4, 5, and then they'd go down 6, 7. Now, when something is full like that, it really wouldn't matter how you wrote them in. You would just know all the boxes have to have 2 arrows, one pointing up and one pointing down. And then 4p, so p has 3 orbitals, so we're going to draw 3 boxes. So these are my 4p's. And it has, it has not 6, it has 5. I hope you caught that too. Sorry. It only has 5. I'll show you if we look back here. See, it only has 5 right there. 6 would be completely full. Okay, so 4p5, so I need 5 electrons, so it'd go 1, 2, 3, 4, 5. So this only has 1 unpaired electron. And then all the rest of them are paired. So how you can think of orbital box diagrams is as a picture. And you do have to remember, though, that S has 1, P has 3, D has 5, F has 7, because that tells you how many boxes. I can't imagine doing anything with F, so don't worry about that. All right, so I hope that having a little more than after learning about it in the main lecture. So in the main video I have of electron configurations, I went over some of this. This should just be practice. So if you need to go back to that video, I think we're in chapter 5, or maybe I'm in chapter 4. I think it's chapter 4. Sorry for any confusion.